So, hello everyone. I'm going to talk about an ongoing research with Daniel, which can be characterized by two fundamental questions. Let's see if I can start with this. Okay, the hierarchies will be fine. So the questions are if there is a better representation of linear algebraic computations than traditional matrix vector operations, and whether we can deduce the optimal memory usage and parallelization from the vector operation itself. So, who cares about this? Mainly researchers who would like to take advantage of the available compute power for their computation-intensive simulations, but who lack the necessary programming skills and hardware insight for really efficient GPU utilization. Such high computation-intensive tasks are very common in physics. For example, the simulations defined by high-dimensional differential equations, which become high-dimensional linear algebraic computations if we solve them numerically. So this is one source of such problems, and they are also frequent in data processing and modeling and statistics. The existing linear algebra libraries generally support a given set of operations that are not really customizable and that are tied to a fixed dimensional structure. That means, for example, I can usually use the matrix multiplication on just exactly two-dimensional structures, and I can hardly, if at all, express expressions like that, where it only differs from a traditional matrix multiplication by a slight extension, but still I can't do that extension to the built-in matrix multiplication. And many mathematicians and physicians face these restrictions regularly. That's why we started looking for an alternative representation or alternative approach to defining and evaluating computations. Our goal is to create a tool that provides a compromise between minimizing the development time and the running time for those researchers who are not programmers. We propose operations that can be nested, and thus they can work in arbitrary dimensions. They can be fine-tuned by their function arguments, so the user's special needs can also be satisfied. We provide a high-level embedded language for the user to build up the expression tree and use a generated C++ program to evaluate the expression. As it was explained in the previous demonstration, the expression trees are a great tool for describing computations because they make it very easy to define and check the relationships between the operations. So we use these representations throughout our processing steps. These are the theoretical and the implementation specific tools we use for our project. We chose the map, reduce, and zip operations as our main building blocks instead of the traditional matrix vector operations. And we use recursion schemes for transforming the expression trees, which are tersely and type hierarchically expressible in Haskell. On the other side, we use C++ to implement data views and to actually evaluate the computation, because there we can express the explicitly define the details of the efficient physical execution. So the simplest of the mentioned higher order functions is map. It just takes an unary function and an array and applies the function element-wise. Zip is the generalization of map for a binary function and two arrays, and combines the two arrays element-wise to get the result. And finally, reduce combines the elements of one array into one element. And two important properties of these three functions is one, that all three of them can be very easily and very efficiently parallelized, and the other is that there are known equivalences available to optimize the expressions built from them. So, for example, if you have consecutive map operations, you can merge them into one just by composing the function arguments. So they are very easy to handle. The question is whether we can really express with these operations complex linear algebraic computations. And for that, this is an example of a simple dot product of two vectors that is defined by an element-wise product and then a sum, and we only needed a zip and a reduce operation. Another important piece of our operation set you can see here is the lambda abstraction, which we took from Lambda calculus to provide the necessary flexibility to fine-tune the previous operations. We store the lambdas in curried form to make partial application possible as well. So we get from the original expression tree to the code that evaluates it in several transformation steps. The first of these transformation steps is the type checking, which deduces the type of each node in the expression tree. And if one operation is not compatible with its arguments, then the type checking can tell it in a form of an error message. After that, we choose which of the vector operations we actually want to run in parallel. There are many different strategies to do this. Right now, we just choose the vector operations that are closest to the root node because this makes the most of the total computation parallel. We allocate the necessary memory for all the partial results in advance. To prepare for this, we need to decide for each operation whether it needs extra memory or not. If it does, then we assign a unique storage identifier to it. If it doesn't, then it means that the partial result of that operation will be stored in a slice of the parent node's memory. After each node got its necessary storage, we collect the storage needs. And for that, we not only use the storage ID computed in the previous step, but also the type of the expression, because in the type there is the size of the partial result, and this means that the size of the necessary memory it's encoded in the type. And the final step is the code generation, where we emit a C++ source code that evaluates the original linear algebraic expression parallelized at the specified points we determine in this step. Recursion schemes generalize the traversal of arbitrary recursive structures like trees in a very similar fashion than as iterators that we use on linear structures. The reason why we built our tree transformations on recursion schemes is that by factorizing out the whole recursion, the purpose of the transformation becomes much clearer, and with the explicit type assumptions that they make possible, it's much easier to implement correct code. So all of the transformation steps I've just shown want to produce a single new value. It synthesizes something, new information from the expression tree and places it on the expression tree nodes. For this analysis, it may need some of the previously produced annotations as well. But when the transformation is performed, there may be other annotations on the tree nodes as well, not just the ones that the actual transformation requires. And this means that the transformation function cannot rely on the exact structure of the tree nodes, but we needed an abstraction which is provided by extensible records. They make it possible to hide this exact annotation set behind a single type parameter, but at the same time we can require the presence of some elements in the annotation set. Well, as I've said, the purpose of the transformation is just to create the new annotation. But for the subsequent transformations, we need annotated trees and not just the result of the previous annotation step. So we needed to bridge this difference with an adapter algorithm that executes the given transformation and appends the resulting annotation to the existing ones on the node. To be able to efficiently process the arbitrary dimensional data in the generated code, we must be able to access the lower dimensional substructures of the data efficiently with minimal cost. For this, we use data views that consist of a base pointer and a stride for each dimension. And with appropriate modifications of the base and the strides, we can achieve efficient transposition, efficient slicing and indexing. For the GPU execution, we use SQL. The main reason behind that is that we extensively use C++ lambda functions to represent the lambdas in the expression tree. And CodePlace Compute CPP is one of the few GPU APIs that supports C++ 11 lambdas. We would be even more happier to use C++ 14's generic lambdas, but that's another story. Another advantage of SQL is that we can very easily switch to like debug mode just by switching from Compute CPP to Tricycle, which is a CPU implementation of SQL. SQL is built on standard C++, which results in a pretty clear generated code, at least on a structural level. We just allocate some buffers as in the example, and then for each vector operation we chose to run in parallel, we produce a comment group, we create the necessary data views, and then run just a parallel for with the higher order functions lambda argument as the acting functor. So the data views are built on a base pointer that we shift as we are indexing the view. which is not possible to do with a single accessor. So we had to pass along the accessor and in the meantime simulate the pointer arithmetic with integers. And at the last level, at the last dimension, we actually query the accessor with the simulated pointer shift. So that was a bit of a workaround, but otherwise we are quite happy with the sequent compute CPU. So the Lambda Gen library helps a lot to the users by providing flexible and various, so easy to use interface, but it also makes easier the work of the library developers, because every intent is explicitly expressible in the Haskell type system. So the compiler finds all the false assumptions, and thus the time spent with debugging is minimal. And the tree transformations built on recursion schemes are very easy to combine and extend, similarly to the vector operations built on higher order functions. So, to summarize our research so far, we did show that it's possible to express linear algebraic computations of any dimensions with just MapReduce and zip. We successfully used recursion schemes as a high-level abstraction for expression tree transformations, and we implemented automatic memory handling with minimal copying and no dynamic allocation, and also implemented the automatic parallelization with generative programming as evaluation. And our next goal is to move on to hierarchical parallelization, because that's the key, of course, to efficiently utilize the GPU. And as I mentioned, we have some optimizations in mind that use the high-level formulation of the expression tree to make such high-level optimizations possible. If you are interested, check out my GitHub page, and thank you for your attention.
Okay, time for questions.
So the question is that you said that linear algebraic problems can be described with the MapReduce and zip. The question is that is this construction efficient enough for real-world applications?
For what applications?
For real-world applications.
Well,
I mean, it's a very simple abstraction, so it is possible that maybe for different problems this kind of abstraction is not efficient enough.
So as far as we only consider linear algebra, I think it only depends on the optimizations. So
on which level? On the order level or the user's level?
On my level, so on how much I can collapse and merge the MapReduce zip operations. So I believe that matrix multiplication can expressed with these can be just as fast as expressed with nested for loops. If I find the correct points to merge these.
Thanks.
Okay, thank you. Any more further questions? Oh, yeah, getting tired. Okay, so then let's thank András again.